Have you ever seen a car hit a barrier and suddenly it stops, or a spring pushes something back? So where does that energy go? So in today's video we are going to understand elastic potential energy, and how energy is conserved in systems like springs. And trust me, this is very important for exams. So let's start with elastic potential energy. So when a spring is stretched or compressed, it stores energy. So this energy is what we call elastic potential energy. So whenever you hear of elastic potential energy, this is just energy that is stored in an elastic material, or we can say this is energy that is stored in a spring or an elastic material after it has been compressed and or stretched. So that is just elastic potential energy. So as we learned potential energy, we say this is just energy of something that is not moving, which is stored energy. Now when you are talking about when we introduce the word elastic, which means that is where the elastic material comes in, and also compression and stretching. So whenever you hear of elastic potential energy, just think of stretching and compressing. And the key formula for elastic potential energy, I made a mistake, I need to put a S here. S that is differentiating it from the normal potential energy. So when we are talking of elastic potential energy, its formula, the main formula is half kx squared, where the u is the elastic the stored energy, which is just the elastic potential energy. What about the k is just the spring constant. What about the x is the displacement, how far it is stretched or compressed. So the thing about elastic potential energy is the more you compress, the more energy stored. And another thing that you should know is at equilibrium, energy is energy is zero. So at equilibrium, so what do we mean when we say at equilibrium? So imagine this diagram. We are going to see this is at equilibrium, like the spring has not been compressed or it's moving to this direction, but it has reached its equilibrium. Like the normal like the normal length of the spring. When here at equilibrium, elastic potential energy is equal to 0. Why is energy is equal to 0 at equilibrium? Because the x is 0. From the formula 1 half kx squared, if x is equal to 0, you are going to find that even the energy will be 0. So this diagram will help you to understand elastic potential energy. And another thing also, when we talk of compression, which means this object moves to the right, it has been compressed. When it moves to the right, it is stretching. So those are the things that you should do. No. So there's usually maximum compression and maximum stretching. So maximum compression will just mean when this spring has been compressed to its full compression, and you're going to find that that's where elastic potential energy is equal to maximum, because x, the displacement is is maximum. So when they ask you where is potential energy, where is the elastic potential energy maximum, it's at end points. It can be at maximum compression or at maximum stretching. Now let's look at conservation of energy. So in physics, energy is never lost and it is only transformed. So just like we said in the previous lessons, like work, energy and power, those are the same principles we are applying even in elastic potential energy, even in simple harmonic motion. So we are going to say that always total energy is equal to is equal to constant. Since energy is constant, that's where we have the formula, or the conservation of mechanical energy formula, which is energy before is equal to energy after. But in elastic potential energy, in simple harmonic motion, we are going to find that the energies that are there, it's energy is just changing from kinetic energy, gravitational potential energy, and elastic potential energy. So we have this formula, which is energy before is equal to energy after. So this is the formula. I said it's going to be rotating through with kinetic energy, potential energy. There are two potential energies, which is gravitational potential energy and elastic potential energy. So as you can see, energy initial is equal to energy final, which means the kinetic energy which plus the gravitational potential energy plus the elastic potential energy of the start should be equal to the kinetic energy plus gravitational potential energy plus elastic potential energy, the final ones. Yeah, so this is the formula that we are going to be using to calculate most of the most of the question. They can ask you to find gravitational potential energy, you are going to use the same formula. They can tell you to calculate maybe the speed, yeah, you can get the same formula, because in one of the energies there is where there is speed. So let's take, for instance, what's there is the example interpretation that I can give is this one. So at the top of a hill here, we are going to find that what's there, the only thing that is present here is gravitational potential energy. Why is gravitational potential energy? Because there is a height somewhere here. As you can see, there is a height. Now, what's the formula of gravitational potential energy? Gravitational potential energy is equal to mgh. So we are going to find its mass times gravity times the height, which means we have the mass of this object, we have the gravity acting on the object, we have the height. So gravitational potential energy is maximum at what? At the top of a hill. What about kinetic energy? Kinetic energy at the top of a hill is 0 because this object is just constant. It's not moving. The velocity is equal to 0, which means the formula of kinetic energy is equal to half mv squared. And this is going to come here when the object is in motion now. As it is moving, it is kinetic what? Kinetic energy. But now when this object moves and it strikes the spring here, maybe it even compresses this spring, that is where the elastic potential energy comes in. That's where the elastic potential energy comes in. So this is how you are going to be the example interpretation that I can give. At top of a hill, it's totally gravitational potential energy. When the object is in motion, it's what? It's kinetic energy. When the object strikes the spring, compresses the spring, it's going to be elastic potential energy. Now let's look at energy in simple harmonic motion. So in simple harmonic motion, energy keeps changing between kinetic energy and the elastic potential energy. Yeah, so we have now what we call the total energy in simple harmonic motion. So the total energy in simple harmonic motion is given by this formula. So in simple harmonic motion, energy is given by half ka squared. What does A mean? So M is just the amplitude. And what is the amplitude? The amplitude is the maximum displacement. So when you are talking about the maximum displacement, for example, this spring compresses like this. Then the object comes somewhere like that. Meanwhile, the equilibrium is left there. So this distance that has moved from here to equilibrium to here, this is what we call A, the maximum displacement. If it's not maximum, it can just be X to mean the displacement. But if that object has reached its compression, we are going to say that it's what? It's A. So that's the A that you are seeing in that formula for total energy in simple harmonic motion. Now let's talk about important energy points. So the first important energy point is at equilibrium, X is equal to 0. And there is kinetic energy there because there is what? Maximum speed. So if like an object is in motion, you are going to find that when it reaches the equilibrium, it's going to it's having maximum speed. And at the end, O is kinetic what? Kinetic energy. So same example also, you are seeing this spring or this object, it's trying to move to the what? To the left. So you are going to see that as it is moving the left, right. Now when it reaches equilibrium, the elastic potential energy is equal to 0, but kinetic energy is what? Is 0 because speed is maximum at what? At equilibrium. So that's the first point that you should know. Yeah, at equilibrium, O is what? Is kinetic energy. So at equilibrium here we are going to say that kinetic energy is equal to maximum. The next one is at turning points. For example, it can be at negative A or positive A. Potential energy is maximum because there is 0 speed there. The object is just it's not moving. So at the end you're going to find that potential energy is maximum. So just as I said in that that's example of a spring that I gave you. Yeah, so for example, it's here. When this object reaches the maximum, there is a so this one, at this, since it's a left side, we are going to say negative a at the maximum what, at the maximum compression. But when we go to the right side, we can put it at a. So these are the turning points. So that's why we are saying at turning points, potential energy is what, is the maximum. Now the last point is in between, when it is not at the end point or it's not at equilibrium. So there is mixture of kinetic energy and what, and the potential energy. Yeah, so that's the third one, mixture of potential energy and kinetic energy, because it is at equilibrium. Because of the same thing, we are going to come up with energy, the formula of energy at any position, which is coming from the same statement of in between there is mixture of kinetic energy and potential energy. So energy at any position is found by energy is equal to kinetic energy plus potential energy. Now let's replace what is kinetic energy. So kinetic energy is half mv squared. What about potential energy? It's half kx squared. Remember, it's elastic potential energy that we are dealing with right now. So here is the formula. Now from energy conservation, I talked over the formula of total energy. So here, which is this, is also total energy. So we are going to replace it by half Ka squared. So therefore we are going to have half Ka squared is equal to half mv squared plus half Ka squared. And this is usually helpful in finding velocity at any point. Yeah, so that's all about energy in simple harmonic motion and elastic potential energy. Now let's go ahead and try to do some examples. So let's start with the first example. So here is our example, which is example 1. So a 13,000 car rolls down a hill from a height of 10 meters and hits a spring which is having a spring constant of 1 times 10 power 6 Newton per meter. Find the maximum compression. B, find maximum acceleration. And you should neglect friction. Yeah, so how do we solve this formula? So this is just what I was talking about, a hill on top of a hill. So the first thing that we should do is we need to convert that weight into mass. We need to find mass. So since we have been given 13 newtons, let's go ahead and find 13,000 newtons. Let's go ahead and find the mass. Yes, so this is our mass, which is 1326.5 kg. Now let's go ahead. The first thing from this one, now write the energy conservation formula that I've given you. Remember, we are assuming that there is no friction, so we can use that formula. So now our job is just to identify the initial. What's the initial kinetic energy, gravitational potential energy, and elastic potential energy? So you are going to find that when the object was starting, when it was still on top of a hill, that is before. So what was kinetic energy? So you are going to find that the kinetic energy is 0 because there was no speed, the object was not moving. So you are going to put 0 here. What about gravitational potential energy? Is it going to have a value or what? So gravitational potential energy, it has a value, so we are going to put its formula, which is mgh, because it has the height. What about elastic potential energy? At the top of a hill, it hasn't like hit the spring yet, so its elastic potential energy is what, is also 0. Same applies for kinetic energy. Even at final, kinetic energy is still going to be 0 because the object is not moving. So kinetic energy is 0. Also, gravitational potential energy is going to be 0 because now the object is not having a height. So gravitational potential energy is 0. For elastic potential energy, it's going to have a value because it now has compression. So we write the formula of elastic potential energy, which is half kx squared. So there we go. Then we just correct the one that are having value. So it is mgh is equal to half kx squared. So that's the formula that we have. Now, what are we asked to find? We are asked to find the compression. So the compression is just the displacement. We have the mass, we have the gravity, we have the height, we have the spring constant. So all we need to do is just make x the subject of the formula. So I've done direct. I've just replaced wherever there's m, I put wherever there's gravity. Yeah. So at the end, we are going to, when we punch our calculators there, we are going to find this. So this is what we are going to find. So we just cancel 500 and we do what is 1/3 over 1/3000 over 500,000. Punch our calculators, we are going to find the answer is 0.26, which is equal to x squared. Now what's the square root of 0.26? it's what? It's 0.51 meters. So that is our what? That is our answer for the compression. So as you can see, guys, we just use the same formula. We just need to identify which one is having maximum, which is having 0. You're getting the point? Yeah. Now let's go ahead and find the maximum, the maximum acceleration. How do we find the maximum acceleration? So for maximum acceleration, we use the formula which is A is equal to kx over m. So let's go ahead again and replace the formulas, the values. And when we replace, this is the value that we are going to get. Acceleration is equal to 384 meter per second squared. So that's it, guys. Let's go and do our final example, which is example 2. So here is our final example, which is just a 2 kg block compresses a spring having a spring constant of 500 Newton per meter by 0.20 meters. Find the elastic potential energy. So what's the formula of elastic potential energy? Potential energy is just half kx squared. So when we replace the values, which is just half times 500 Newton per meter times 0.20 squared, the answer is going to be 10 joules. What about kinetic energy? So for this one, we are going to see like for kinetic energy, what's the formula of kinetic energy? Kinetic energy is equal to half mv squared. Now what you should know is since it's simple harmonic motion, all elastic potential energy is going to be converted to kinetic energy, which means the value of kinetic energy, we can just say it's equal to 10 joules, because all elastic potential energy is going to be converted to kinetic energy. Replace, it's going to be 10 is equal to half. What is the mass? The mass there is 0.2. What about the velocity? That is what we want, v squared. Oh, sorry, the mass is not 0.2, it's 2. The one that is 0.2 is the compression. Yeah. So when we calculate that one, we're going to find that our v squared is going to be equal to what? Square root of 10, which is just equal to 3.16 meter per second. So that is what? That is our speed that we found by writing the formula for kinetic energy. So thank you guys for watching, and don't forget to subscribe for more lesson videos and academic tips. So